Did you, Kevin? Did you found how to do it? Kevin, could you please put your microphone on because we need to hear your. Oh, I see Yvonne has connected. Yvonne, I'm happy to see your connection. Oh, and Kevin is able to share slides. Very good. Kevin, you need to unmute your microphone so that we see your voice and explanation of the slides. I will send a brief email just in case you do not hear. Kevin, can you please say something? I see you unmuted the microphone, but I do not hear you. No, we do not hear you. I see you're typing in the chat room. Oh, there is some sound. Is it Kevin? Now I have muted my microphone. Now I'm unmuting. There is a little button mute and unmute the microphone.
Followed by the pound key. You will be placed into conference when the moderator arrives.
I believe Kevin is trying to log in and log out, and hopefully he will be connected soon. Mm-hmm. Mm. I'm sending another email to Kevin to check if he's going to reconnect.
All right, hello, can you hear me?
Yes.
All right, good, yeah. I don't know what happened. I tried calling that number. I tried on that live video chat thing, so I'm not sure what went wrong.
Okay. You next time or after we complete this meeting, you may try once again. But please, I think the best time investment right now will be if you go over your slides and we ask questions if there are some. And I hope that recording will be successful so that you can hear this feedback after. Also, please give me notes, commands when I should go to the next slide, and I will just project them.
All right.
So right now we are on the first slide, and you may, if you are not on this joinnd.gov, you can just open your slides on your computer and tell me when you're going to the next slide.
All right, you can still hear me, right?
I did put the first slide right now, and anyone who is on our connection, I see at least Yulun and maybe someone else is in the room. Will see the slide and hear your voice, and I hope it's also goes for the recording.
All right, give me a quick second.
Mm-hmm.
All right, you can hear me, right?
Yes.
Okay, and you have the slides that I sent to you?
Yes.
Okay, so I didn't get a chance to complete all the slides. So at the end of this, you have the current figures thing I sent you, the Word document.
Yes.
All right, so yeah, at the end of this presentation, switch over to that Word document. I'm going to continue it.
Okay.
There.
Okay, you can do so.
Okay, so here goes. So I'm studying excited state dynamics in one-dimensional thermoelectric materials. All right. So before I get into the specifics, why is charge transfer important? Why are we studying this? One of the most important applications is to semiconductor devices. Semiconductor devices are used in everything. So studying charge transfer, or another way of putting it, is the movement of electrons, how to improve the rates. So studying that will greatly improve the efficiency of semiconductor devices, and will make our everyday living easier. So that's one reason to study it. Another reason to study it is it gets us into non adiabatic dynamics, which takes into account nuclear motion, nuclear vibrations, and how that affects the orbitals. So that's one very important theoretical aspect. And as stated earlier, improving charge transfer helps us build better conductors and semiconductor devices. So that's why charge transfer is important. And then next slide, we're going into photovoltaic.
Should I go to slide number 2 and slide number 3?
Slide number 3.
Okay.
Does it say photovoltaic?
Yes.
All right. So continuing on. So photovoltaic process is essentially using lights to excite the electrons, so they have energy to go into orbitals with higher energies. So in this example, I'm showing you have sunlight from the sun. It's shining on a semiconductor, so that sunlight has photons. It excites the electrons in that semiconductor, and the electrons are moving, so therefore they're creating a current, and that current powers that light bulb you see. So that's an example of the photovoltaic process. Next slide.
Kevin, this Image doesn't show details of the specially treated semiconductor material. One may need more details. I'm making the notes and
Okay, I'll update the picture.
okay, I'm going to the next slide.
It says thermoelectric, right?
Yes.
All right. So that's the photovoltaic process. The process I'm studying, in contrast to that, is the thermoelectric processes, namely nanowires, semiconductor nanowires that use the thermoelectric process to induce a current. So what we have here is, on one side we have a hot side, and on the other we have a cold side. So you have electrons on the hot end. The electrons have greater kinetic energy because of the hot end, and then they move to the other side, to the cold end. And then when enough electrons gather on that a cold end together, they produce an electrostatic field that repels the electrons on the other end. So you have electrons on one side, and you have electrons on the other side, and that produces a voltage, and then that produces a current. So that's picture A, and then in panel B, you see that the thermoelectric effect is being used to create a current inside in that circuit. So you have a current, and you have a resistor, and you have electrons on the hot end and the cold end. And as I said before, in between those electrons, you have a voltage, and then that produces a current. So that's how the thermoelectric effect produces a current, and that's what I'm studying.
Okay.
Next slide.
Yes. Next slide is ready.
Did you say something?
Yes. Next slide is ready.
Okay, it says lead telluride nanowires, right?
Yes.
Okay, so which brings me to my to what I'm studying. So I'm studying the thermoelectric effect in lead telluride nanowires. So why am I doing that? Why am I studying them? Namely because they have a great potential as a thermoelectric material to be used in semiconductors. It's been widely researched for around 5 to 10 years now. Many researchers are impressed with its potentiality. However, a lot of challenges remain. So there remains a huge gap between this potential and actually applying it. All right. So this is why. Yeah. So one of the things researchers do to increase lead telluride's electronic properties and its conductivity and its charge transfer is we dope these lead telluride and nanowires in various things. So specifically, I studied doped lead telluride nanowires. All right.
Mm-hmm.
Next slide.
Okay.
It says doping, right?
Mm-hmm.
Okay. So you can still hear me, right?
Yes.
Okay, so before I get into the particulars about what my lead telluride nanowire was doped with, I just want to go over the entire process of doping real fast. So here you on panel A, you have your conduction band, valence band. Nothing special is happening there. And then on panel B, you have your sodium doping. So what happens there is that the valence band is being emptied of one shell, and then in panel C is your iodine doping, where the conduction band is being filled by one shell. All right.
Mm-hmm.
So that's doping in 2 minutes. Next slide.
Yes.
All right. It says my doped nanowire, right?
Mm-hmm.
Okay. So what we have here is my doped nanowire. The two pink atoms on the top side is my iodine, and the two bottom charges is my sodium. All right.
Mm-hmm.
So why did we choose these two per particular elements? All right. Before I can answer that, I need to talk about the chemical structure of lead and telluride. All right. So in a regular lead telluride nanowire, lead has two extra electrons in its valence shell, and telluride needs two extra electrons. All right.
Mm-hmm.
So in a regular lead telluride nanowire, lead donates its two electrons to telluride, and they form a nanowire. All right. So when we're doping these with the sodium and iodine, the sodium in this case replaces the lead because the sodium has a one extra electron in its valence shell, and the iodine is missing one electron. It needs an electron to fill its outer shell. So the sodium replaces the lead, and the iodine replaces the telluride because sodium donates its extra electron to iodine, so they both have full shells. All right, so that's why we use iodine and sodium as dopants.
Kevin,
Okay.
can I ask in the middle?
Yeah, sure. Go ahead.
So, why you add doping? You may have said it, but you may want to highlight it once again. What is the reason to add doping?
We add doping to increase its electron properties, specifically the charge transfer. So the charge transfer is the main property that we're going for. In a regular undoped lead telluride nanowire, there's like hardly any charge transfer, so it can't be used in a semiconductor devices. You can't conduct electricity through them, or you can hardly conduct electricity through them. But if you dope them with sodium and iodine, the charge transfer increases significantly. So, and you have a lot more potential of it being used in semiconductor devices because it can conduct electricity better. So that's why we dope the nanowire with the sodium and iodine.
Excellent. Thank you.
But why you have two dopants?
What?
Why you have two dopants?
All right. Okay, so next thing are my methods. So I'm studying charge transfer in doped lead telluride nanowires at different temperatures.
Wait.
So,
Kevin, did you answer the question of Dr. Khanov, Yulun? Why do you need two dopants instead of one? Why there are two elements are used for doping?
Just a side note, I couldn't hear him. So when he asks the question, you're gonna have to ask it for him.
Oh,
so I can
okay. Yes, because it is a Skype. Yulun, sorry, I will repeat his question, your question once again to Kevin. Yulun is asking, why do you use two elements for doping instead of one?
I assume that the number of dopants you're using is directly correlated to its charge transfer rate. So the more dopants you use, the more charge transfer you get.
I interpret his question differently. Not the number. He is not asking why there are 2 sodium and 2 iodines. He asks why you are using both sodium and iodine instead of having only sodium or only iodine. Why do you need a pair of elements?
Um, o- okay, because the sodium and the iodine go together. So basically, when the sodium and iodine are near each other, the electron from the sodium is going towards the iodine to fill iodine shell. So that that extra sodium electron, when it's moving from the sodium to the iodine, that's actually what's happening in the charge transfer. All right. So if
Okay.
you only have like
Uh-huh.
iodine, or if you only have like sodium, that electron wouldn't be moving. So therefore, there would be no charge transfer.
Okay, so let me try to interpret it reward. In order to facilitate charge transfer, one needs to have donor and acceptor, a pair of donor and acceptor units. And iodine and sodium doped segments of your nanowire serve as donor and acceptor.
Yeah, that's correct. I guess that's a more technical way of what I'm saying.
Okay, very good. Okay, should I go to the next slide?
Yeah, sure.
Okay,
So,
I'm on slide 8 with methods.
all right, got it. So methods. So I'm studying charge transfer with lead telluride nanowires. So how am I studying them? What methods or what equations or theory am I using? All right. So first things first is I'm using density functional theory. Quick question. When I'm giving my seminar, should I assume everyone knows what density functional theory is, or should I give a brief explanation?
You should give brief explanation. Because most of the research groups at the Department of Physics deal with soft condensed matter and force field or coarse grain molecular dynamics. So if you provide short summary, it will be appreciated.
All right. So density functional theory in about a minute or two is in regular quantum mechanics. We're dealing with the regular old wave function. But however, as time went on, experimentalists and theorists found that it's that wave function is very difficult to use in calculating expectation values due to its ubiquitous and mysterious nature. So they found it easier to just work with density values. Specifically, if I remember this right, the amount of charge per unit volume, and just use that density to calculate expectation values.
Okay.
All right.
Okay.
All right. Yeah. So that's what density functional theory is. It's just an easier theory and method to find expectation values. So I used a density functional theory with a computer software called VOSP. All right, so I used VOSP to compute all my expectation values. All right, and then I used my non-adiabatic couplings to see how my energy and position expectation values change with time. So before I go any further, I should explain what non-adiabatic dynamics are. All right. So in the regular adiabatic approach, you have your nucleus and your electrons. So nuclear and electronic states. All right. So in the adiabatic approach, we assume that the nuclear state isn't influencing the electronic state, when we make that that assumption, things are so much easier to calculate. All right, but then if we make this assumption, we find that we can't explain certain things, like when I'm studying charge transfer. All right, so when we take into account how the nuclear states is affecting the electronic states, that's what we call non-adiabatic dynamics. All right. So essentially, when the nucleus vibrates, it's essentially changing where the orbitals are. So in regular adiabatic dynamics, the nucleus isn't vibrating; it's changing, it's staying still, and therefore its orbitals don't change in time. So the expectation values don't change in time. However, the non-adiabatic approach, we're taking into account those nucleus vibrations, and we're seeing that the orbitals are changing with time. Excuse me. So that's what non-adiabatic dynamics is. All right. So moving on to transition rates. I use the Redfield equations of motion to find the transition rates between my orbitals using that equation right there. All right, and then I use that my Redfield calculations when I'm calculating my density matrix dynamics. That R sub dis is my Redfield operator. And there you see my commutator between the Hamiltonian and my momentum.
What? Commutator between Hamiltonian and what?
Oh wait, that P isn't momentum; it's a charge density. Right?
Yes. And when you were introducing the DFT, you were telling that everything depends on density, right?
Right.
So, is this density the same as you mentioned in the while introducing DFT, or there are some differences?
It's the same.
Well, it's very close, but when we solve dependence of density on time, it will be density that corresponds to transitions from state to state, and the density that is used for DFT is only for equilibrium. So there is a question, there is a little homework for you to decide how similar and how different are densities in the ground state DFT and in the density matrix equation. And feel free to consult any group members, collect different opinions, because it is an important thing. We shouldn't waste time right now, but please put it in your list to do.
All right, got it.
Okay.
All right. Next slide. So you're on the observable slides, correct?
Just a second. Okay. Observable slide.
You can hear me, right?
Yes.
Okay. So so next are my observables. How did I calculate my observables? So specifically, my observables are the energy and position of my electron, and using non-adiabatic dynamics for certain initial conditions, I'm studying how my energy and position expectation values are are changing with time. All right. So essentially, when I made my graphs of when I studied how my energy and position expectation values were changing with time. Um, from there, I calculated my electron relaxation rates and electron hole relaxation rates. All right. So those relaxation rates are essentially, think of them as how fast it takes for the electron or the electron hole to return to its original ground state orbital. All right. So there are two different expressions for these relaxation rates. Um, so there's the differential form. So we're finding out how the energies of the electron and the electron hole are changing with time. So that's the regular classic approach to it. But the actual way with which my MATLAB code calculated my relaxation rates was with the integral form you see below. So if you use simple calculus from calculus 2, rearrange that differential form and turn it into an integral, that's what you would get. So that's how MATLAB calculated my observables with that integral form. All right.
Mm-hmm.
All right. Let's move on.
Yes, before we move on, I want to ask a question, if you permit.
Sure.
So there are 4 bullets here in your observables, and so first one is change of energy and position, right?
Mm-hmm.
Second one, expectation value of electron and hole energy, and then last 2 are differential and integrated fitting formulas. So for the first 2 bullets, you are not showing equations. Do you plan to add them?
Yes.
Do you need help? Do you have an idea where to take these equations?
I have an idea. I think I know what to do. If I need help, I can always ask one of you guys.
Okay, thank you. For the bullet number 2, expectation value of electron, can you share your vision where it is taken? Just verbally explain where the expectation value of electron as function of time is taken.
I don't understand your question.
Okay, I will explain. In the bullet number 3 and 4, in the bullet number 3, you are taking time derivative of expectation value of electron.
Right.
Where this expectation value of electron is taken from? This angular bracket capital E sub electron. How it is computed?
Okay, so from what I understand it, we use density functional theory or VASP to calculate the expectation values themselves. And then after that, we take those expectation values and then we use non-adiabatic dynamics / the MATLAB code to see how these expectation values are changing with time.
You're not telling, what you're telling is not wrong, but it doesn't help. Like if I never did these calculations, I cannot learn from you how to do it. Can you be more specific? Like on the previous slide, you explained how to solve Redfield equation, the equation of motion for density matrix. So at the end of the previous slide, you obtain density as function of time, or maybe density matrix rho mn as function of time. How does the knowledge of these objects allow to compute the expectation value of electronic energy. So as a result of solving equation of motion for density matrix, you are getting occupations of each orbital versus time.
All right.
How does this information, how does this occupations of orbitals is converted into energy of electron as function of time? Please record this and add this to your plan. So either by equation or by verbal explanation.
Okay. I'm gonna guess that. So you have the occupation number, the occupation per orbital. Do you somehow take an integral over each orbital so you find the number of electrons in each orbital? So I'm guessing you take some sort of integral to find the number of electrons in each orbital.
No. It is much simpler. It is much simpler. You multiply energy of orbital number I times occupation of this orbital number I at specific point of time. And then you make summation over orbitals in the conduction band. So this equation will give you expectation value of energy as function of time.
All right.
Okay?
Got it.
Good. So now I'm going to open your figures, and I am on the figure 1, and I think you want me to go further. Now I'm on the figure 2, and I think you want me to go further.
Go to figure 3.
Okay, now I am on the figure 3, yes. Please go ahead, explain it, and give me sign when I need to switch to different figure.
Right. Okay, so we have the density of states. The density of states is defined as the number of states per interval of energy. So let's look at panel A first. In panel A, we have the density of states of a regular undoped a red rectangular lead telluride nanowire. Okay. So if we look at it, we see that the band gap there is approximately like 0.5 electron volts, and then we see it has conduction and valence band. All right. So let's compare it to figure B. All right. In figure B, we have the density of states of a nanowire that's doped with iodine and sodium. All right. So two things should pop right out of you. One, the band gap for this doped lead telluride nanowire is way bigger than the undoped one. All right. So a bigger band gap means that.
Wait. Kevin, can I ask?
Yeah.
While creating the image for density of states, one is using the width parameter, the broadening of the Gaussian function, right?
Right.
In order to compare two density of states figures, one needs to make sure that the width parameter for first and second was the same. Did you check? Because you are making conclusion that with dopants the gap becomes broader. It is a little unexpected. And in order to support this, how to say, controversial statement, one needs to make a proof or to make that width parameter for A and B was the same. From the visual appearance of the figures, it seems to me that the width parameter for the panel B is smaller than, and the width parameter for panel A is bigger, and the Gaussian tails for larger width and for smaller width artificially affect band gap. So it is not the. Did you try to compare energy of HOMO and energy of LUMO for these two cases to support your statement that gap for the doped becomes wider?
No, I didn't consider the width of these two graphs.
Okay, please do a little research about width and for literal comparison of the gap. Energy of LUMO minus energy of HOMO for A and B. Okay?
All right. Got it.
Okay, thank you. Please keep going.
Okay, so next thing is I'm moving on to figure 4, which is the absorption spectra.
Mm-hmm. Mm-hmm.
Give me a quick second.
Yep.
Okay, so if we look at figure 4, that's our absorption spectra. So it's essentially like how much light an electron has to absorb to move on to the next energy level or the next orbital. So if you look at figure 4, an electron absorbs the greatest amount of energy when transitioning to orbitals, ranging from 1.5 to 2 electron volts. Excuse me. All right. Another thing to note is if we look at transition on number 1 in figure 4, we note that that's the lowest transition there, and it's dark. This is what we expect since the electron is transitioning to a higher energy orbital there. So the absorbed photons, they look like a dark transition there because the photons have been absorbed by the electron, and they're not really emitted as a visible light. All right. So just wanted to make a quick note about that. That's why number 1 is a dark transition. All right. Do you have any questions about this figure?
I'm fine with this figure. Maybe you or Fatima have. If they ask question, I will retranslate it to you.
Okay. Let's move on to figure 5 then.
So there were no questions. I have a brief question about do you have a spectrum for undoped, just for comparison? It's not critically important, but I just have a curiosity to see will they be very similar or very different. But it is like it's not a primary goal. It is only if time allows.
All right. I can see if I have it really quick.
Okay.
What, like in the evening or something.
Yep.
Yeah. Any other questions, or should we run the figure 5?
I think everyone supports your move to figure 5.
All right. So yeah, let's move on to figure 5. This is the fluctuation gap. All right. So this fluctuation graph is showing how the energy of each orbital. We're looking at changes with time. Save your conduction and valence bands there. One thing that's of key interest there is how the band gap changes with time. So initially at time t equals 0, you start out with the band gap of I'd say like 1 electron volt, but then as time goes on, the band gap decreases until it becomes 0. Um, this these results seem to agree with the red field tensor graphs, which we'll look at later on. So basically, the band gap decreases with time because of the following reason. All right. So we're looking at the nucleus and the position of the nucleus. Since it vibrates, it changes with time. All right, and we know that the energy of each orbital depends on the position of the nucleus. So therefore, by this simple chain rule, because the energy depends on the nucleus, it has to also depend on the time. All right, so that's why that band gap is changing with time. All right. I know that this is of great interest, and I know for this figure I have to find out what temperature this fluctuation graph is made of. So that's one of my top priorities right now.
Very good. Very
Any
good.
questions about this figure?
I don't hear more questions. As a secondary priority, you may generate such figures for all temperatures that you have explored to see how it goes for, if you check for 300 Kelvin, 500 Kelvin, and so forth. But again, you have something more important. Put it as a secondary priority.
Okay. Just a quick second. All right. I'm going to move on to figure 6.
Okay.
These are the Redfield tensors at various temperatures. So if you remember last week, I had a huge paragraph there. I just deleted that and put that in my results. I mean, I don't know. It just all that information seemed like a greater fit in my results section. All right. So I just wanted to make a quick note of that. All
okay.
right.
Kevin,
So
Kevin, may I ask before you start?
Yeah, sure. What's your question?
Connection to Fermi's golden rule.
For me, so golden rule. Oh shoot, this was in my undergrad quantum class. I remember we covered it near the end of the semester. Does it have to do with transition rules between orbitals, or?
Yes, you may want to explore this question and find your own words, but in very basic, the protocol to convert non-adiabatic couplings into these Redfield tensors that you are showing right now is very similar to Fermi golden rule. So basically, all these skyscrapers that you are showing are Fermi golden rule rates for different initial and final states.
All right.
And if you tell this the majority of physics faculty will be very happy to accept this explanation.
All right, got it. I will definitely make a note of that.
Okay, thank you.
All right. So, moving on. If you look at my figure, if you look at the initial temperatures, 300, 500 Kelvin, the transition rates near the band gap are close to zero. So near the HOMO and LUMO, you don't see any of those skyscrapers, or the skyscrapers are really small. So the transitions there are zero. However, if you, as the temperature increases, we see that transition rates for orbitals near the band gap experience an increase until when we get to 1100K, the transition rates appear to be, for the most part, homogeneous among all the orbitals. All right. So, in my opinion, I kind of expected this, and I expected this because of the following reason. As the temperatures increase, the electrons will have more energy to jump between the orbitals. And then as the temperature increases, the gap between the conduction and the valence band decreases, as we saw in my last graph. All right. Okay. So another thing that I wanted to point out is that, hold on, give me a second. All right. I just wanted to point out that the results we're seeing in Figure 6 correlate very highly with what we saw in the last figure, which was my fluctuation graph. So we saw that as time increased, the band gap became smaller and smaller and smaller. We see a similar thing happening here with the red field tensors. We see that as the temperature increases, the band gap becomes smaller and smaller and smaller. All right.
Mm-hmm.
So I just wanted to point out that this is a feature that these two figures have in common. All right. Any questions about this figure?
I do not.
All right.
I don't hear. Okay, let's go forward.
Okay. So this is Figure 7, orbital localization. So here we see the orbitals that I looked at in my studies. One quick thing to note is that my electron hole orbitals are localized near the sodium dopants, and then my regular electron orbitals are localized near the iodine dopants. So I just wanted to very quickly point that out. And then here we got Figure 8. This
Kevin,
is my,
Kevin, a quick question.
Yeah.
What was the principle to select these specific orbitals?
Okay, so I selected these orbitals randomly, and now I realized that it was a mistake. If I had a chance to go back in time and do things differently, I would look at orbital transitions with the greatest oscillator strength.
Okay. But even with this random selection of orbitals, you see a specific trend that most of the unoccupied orbitals are localized on iodine, and most of occupied orbitals are localized on sodium.
Right.
Good. Very good.
I have a question. Are they based on different atomic models? Because it seems the atomic position also changes. Why is that?
Even I need to reproduce your question, and I need to understand it. So Yun is asking why positions of atoms are changing while going from orbital to orbital. Is Yun, is it what you're asking?
Yes.
Kevin, do you understand the question?
So the question is why atomic position is changing when going from when the electron is moving from orbital to orbital.
Yun, is Kevin formulating your question right?
Yes.
Yes, Kevin, please answer it.
Okay, so if I understand this correctly, it's not the like atomic position that's changing, but it's the nucleus's position that's changing. Right. So the nucleus is vibrating, and that nuclear motion is what's changing the position of these orbitals.
No. I respectfully disagree. I think the all orbitals are computed for the ground state 0 Kelvin temperature, and the difference in atomic position comes because of the human error in placing images into the stable and changing the aspect ratio. So it is an artifact that ideally should be fixed.
Okay.
I understand that Kevin probably wants to practice higher quality artistic design of the images and fill all white space with figures. But scientifically, it would be really beneficial if the aspect ratio, like ratio of x to z of the tube, is not changing, and it shows cubic symmetry of all nanowires. Also, it is it looks like Kevin is using perspective option for plotting, while orthographic is a little less pretty but easier for comparison. But this is my personal preference. I prefer orthographic. But Kevin, do you hear this feedback?
Yeah, I'm hearing it.
Okay, so you decide whether you want to slightly change the figures or you just verbally explain what you're doing. But question of Yulun was very natural. If it is the same system with different orbitals, why the atomic positions, why the structures look slightly different from orbital to orbital?
All right, I'll keep that in mind.
Very good, very good. Thank you.
All right, I'm going to move on to the next slide. This is my waterfall slide. This shows the conduction and valence bands with energy and position. And I'm not sure what goes on the z-axis. Is it occupation number?
This is integrated partial charge density. It is you may give an equation for it. It's not occupation. It is absolute value squared of the given orbital. So it's probability density or charge density for specific orbital, and all orbitals are defined as function of three-dimensional coordinate. But
So the z-axis is the charge density squared for each orbital.
exactly, very good, very good. But here is a little logical paradox. Each orbital is a function of three variables, x, y, and z, right?
Right.
But here we are showing only dependence on z. So in order to obtain dependence on z, one needs to integrate the three-dimensional dependence on x and y, which gives the density of orbital number I as function of z coordinate. And for one-dimensional systems, it is very preferred for this charge transfer over interface. It is very appropriate analysis.
All right, got it. Next slide.
Just a second, I'm making some notes on your slides.
All right.
And also, what is the band gap of this material? Because from density of states, it seems like 0.5 nanovolts, right? Here, the band gap it seems 0.8.
Yulun is asking what is the band gap of this material, and Yulun tells that from the image it looks like the gap is about 0.8 electron volts, and in your other images it seems to have different values. Can you please comment about value of the gap?
My guess is that the band gap is the same in each figure, but the band gap just looks different in each figure, or it appears each different between the figures just because of the way the figure is oriented. So I believe that figure 8 is oriented in a way that makes the band gap appear more bigger than it really is. That's my opinion on it.
I'm not sure. Let me share my opinion, which also can be wrong. When Kevin was showing density of states, each HOMO and LUMO orbitals accumulated additional width because of the line broadening, and the energy offset between centers of this Gaussian peaks is actual gap. But if one visually analyzes an offset between edges of this Gaussian profile, it will show some not correct value of the gap, which is smaller than the actual gap.
Okay.
Does it make sense?
Mm-hmm.
Okay, very good. Kevin, I think we are done with this question. If you don't have other comments.
Okay. So I'm moving on to figure 9, dynamics of charge density distribution as a function of energy. Mm-hmm. So a couple of things to note. If you look at the lower temperatures, particularly by 300 Kelvin, you notice that the change in energy, the relaxation rates, which is the derivatives of those lines you see there, are almost negligible. They're almost zero. They're essentially a flat line. So there's almost a no change for for the lower temperatures there. But however, as you increase the temperature, the relaxation rates
Yes.
all right. Just a quick second.
Uh-huh.
Okay, I want to point out that there's one curious trend from these figures. I would expect that the magnitude of the energy difference between the electron and the hole and the temperature would be directly proportional to each other. All right, let me rephrase that. I think that the energy difference between the electron and the hole versus the temperature, they should be directly proportional to each other. However, the opposite happens. As the temperature increases, the energy difference between the electron and the hole decreases. All right. So I just wanted to say that this trend seems to agree with Figure 6. All right.
Mm-hmm.
Figure 6. Those are my Redfield tensor graphs. So what the trend you're seeing here agrees with what you're seeing in Figure 6.
Mm-hmm.
Any questions about this figure?
Well, I have some limited skepticism, but in the remaining time before your Monday seminar, there is no time. I would maybe after your seminar we may try to double check about my most specific concern is that especially in your data for 1100 Kelvin, the energy of electron and hole converge to zero. I hear your explanation, but still it is a little surprising to me, and I wonder if it is a true result or it can be an error in either code or human error in using the code. So later on we may double check. If it is so, I wouldn't be against it, but this is interesting result that we need to double check with special care, maybe after completing your seminar.
All right.
And also, I guess you need to double check data for 500 Kelvin and 700, because from the band gap, it seems these two data should be swapped.
Kevin, Yulun suggests to check data for 500 Kelvin and 700 Kelvin, and he thinks that this data may need to be swapped. Just double check if labeling and placing of images into the table correspond to what they actually are.
Okay. If there are no questions, let's move on to the next slide. Figure 10. So we're seeing how the charge density changes with the position.
Kevin, please try to be closer or further away from the microphone. Right now, the sound is a little bit blocked.
Okay, can you hear me now?
Oh, so much better. Yes.
Okay, so in Figure 10, we're seeing how the charge density changes with the electron's position in space. So if you take a quick qualitative look at the graph, you can draw two conclusions. First of all charge transfer is localized near the iodine dopants. If you remember my spiel about doping earlier, it's to be expected. So the electron from the sodium is going to the iodine. So the sodium is the donor, the iodine is the recipient. So it would make sense that the charge transfer will be localized near the iodine dopant. That's something we expect.
Mm-hmm.
All right, and then another thing to note is that as the temperature increases, the magnitude of the charge transfer also increases. So to put it in layman's terms, as the temperature increases, the electron travels greater and greater distance. All right.
Okay.
And then, all right. So yeah, those are my two main findings for my position graphs. Any questions? All right. Let's move on to figure 11.
Okay.
All right. So actually, we're going to look at figures 11A and 12A. So we're looking at how the relaxation rates are changing.
Okay, just a second. If you want readers or your audience to look at 11A and 12A at the same time, you may want to rearrange your figures, and in figure 11 to put both electrons and holes panel A as function logarithm as function of energy distance difference.
Okay.
And then in the figure 12 put both electron and hole as function of temperature, because it is there is nothing wrong scientifically, but aesthetically for the visitors of your seminar it is not possible to jump to refocus on one slide and another slide so quickly. So please consider when you will be doing slides, and maybe for the figures for the paper as well, realign, replace the panels, like put dependence on energy difference on figure 11 and put dependence on the temperature on figure 12.
All right, understood.
Okay, good.
Okay, so in both the 11A and 12A, we're looking at how the relaxation rates for the electron and the electron hole change with energy. So if we look at 11A, which is how the relaxation rates for the electron change with time, it appears that the band gap law is only applicable to at higher temperatures. At lower temperatures, from the data I have there doesn't seem to be that much change with energy. So that's one conclusion I can draw from this. And then if we look at how the relaxation rates for the electron hole change with energy, which is a 12A, we see that the band gap law has a limited applicability to these results. All right. So I just wanted to very quickly point that out. And then the last two figures I want to look at is 11B and 12B, which is how my relaxation rates change with temperature. And the key to take away from this is that the rate of change of my electronic relaxation rates with temperature is independent of orbital transition. All right. And that means that no matter what orbital transition you're looking at, they all change with respect to temperature at exactly the same rates. All right, that's the main conclusion I drew from that. So if you look at those graphs, they specifically look like Boltzmann distributions. All right. So then, if you look, so then if you remember, the band gap law is a e to the negative alpha delta E, where delta E is my change in energy. From these graphs, we can infer that alpha is 1 over kBT, which is the 1 over the Boltzmann constant times temperature. All right. So that's the key a takeaway I took from these graphs. And then that's my presentation. Thank you.
Okay.
Any question?
Thank you, Kevin. That's everyone is applauding to you. So, do you have conclusions for the slides? I understand that for the paper it will take special effort of writing, but do you have a slide for conclusions?
I don't have a slide for conclusions yet.
Maybe it is a priority number 0 above 1 and 2.
Okay.
When you will relax after today's session, first thing to do is to design conclusions slide and put there maybe more than one slide. Put there as much as possible information, maybe in form of graphical or schematic diagram, like what is the main message you want audience to take home.
I understood.
Okay, let's check if Yulun or Fatima have questions to you.
I don't have any question.
Okay, Fatima doesn't have question, and Yulun doesn't share questions as well. Okay, then many thanks to Kevin for making this effort of presenting. I think for the group meeting we are done for this week, and I'm just letting know Kevin, and if anyone is interested, tomorrow at 5 we will make one more meeting in the same format where Kevin will make another dry run of his talk, right?
Right.
Yes, I hope by this time there will be more updated slides. Everything will be in PowerPoint rather than in Word. And on Monday, 3 p.m., there will be, I don't know, physics seminar coordinator should share the link. I don't know how they will organize it, but our business is just to help Kevin to be ready for presentation. They probably will do similar format as we do right now, or maybe they will have something more outstanding.
All right. So my homework between now and tomorrow, when I give my second talk, is to make my conclusion slide. You said that's priority 0. And are you going to email me the notes you took?
Yes. I will share with you. And since I've got your materials shortly before the meeting, I didn't share it with group members, but with your permission, I will share it with everyone. And if group members have some constructive suggestions, they will directly share them with you.
Yeah, definitely.
Okay, very good. And so the this payload of Kevin's talk is being on the way to the right orbit, and for all of us, we should start thinking about next week Tuesday when we will be doing results section for the papers, constructive editing. We need to combine our old tradition of helping each other to edit in presence of each other. Maybe we can do it virtually if everyone sends materials early enough. I'll share it between group members, and we'll create quick notes, and then on the meeting we will project notes and share share comments. I understand that it is a little bit boring, but it is. It seems as a most productive way for high quality manuscripts with high rate of acceptance. Okay, I think we are done. I'm also going to check if recording went well, and if it was, I'll share it with all group members. And for Kevin, definitely see you tomorrow at 5 at the same link. And everyone is welcome to join if there isn't enthusiasm, but it is not necessary. I think comments from today were sufficient. Tomorrow will be just a dry run, and everyone is invited to the group meeting next Tuesday for 4 p.m., which we will do, I think, again in the electronic form.
All right. Good night.
Good night. Fatima, I've got your message, and I'm planning to, as promised, submit within this month.
Okay, good. Actually, I thought that there will be no group meeting today since it's a spring break, so I didn't check my email. I saw the email at 4:30, then right away I joined.
Oh, do not worry. It is mostly to help Kevin because although he is on the introductory stage of his research, physics seminar was short in speakers, and they offered him to do this, so we need to help him.
Okay.
One day I will nominate you to be the speaker on the Department of Physics seminar. Just keep it in mind, and you will need to prepare to show the best you can.
Okay. I have another question.
Please.
So this graphene paper, so are you planning to submit in Journal of Chemical Physics or somewhere else?
I think Journal of Chemical Physics, Physical Chemistry. Chemical Physics is Journal of Chemical Physics has a lower impact factor, but they are more serious, more meticulous about derivations and equations. So it is more physical chemistry is better target.
Okay, so this result is enough for physical chemistry.
Yes, I think. Well, as while polishing the presentation, we may add something, but I think we shouldn't slow down the speed. I have in mind some very bright and promising projects, and we should finish with this one and go to the next one, and maybe when I meet in person with Venji, we will have some productive ideas. But the pure graphene with K with this magnetic field seems to have sufficient amount of data to publish, forget, and go to the next stage.
Okay. So for Journal of Physical Chemistry, there is no particular deadline, right?
Right.
Okay.
But still, I'm putting the deadline of last day of April for all of our manuscripts, same as if they would be for molecular physics, because for summer break there could be very different plans, and who knows how arrangements will be done with this social distancing. So we better complete things during the semester and then focus on new projects.
Okay, good. Okay, I can finish. I think I can finish by April.
Excellent.
Not a problem.
Super.
Yeah. So I will send you a result tomorrow. I'm working on it.
Okay.
I thought that I could send you today, but
do not worry. We will do the group discussion on next Tuesday. But if you send it earlier, I will try to work on it ahead of time and come prepared to the Tuesday session.
Oh, yeah. Okay.
Okay. Yeah.
Okay, sounds good.
Yuan, do you have anything to discuss?
Not really.
Okay.
And right now, I'm just working on the proposal.
Oh, you did some changes to the proposal?
Yes.
Excellent, excellent. Thank you so much. This is very, very appreciated. And
So, ideally, how many pages do we need for this proposal?
this is a standard size of 15 pages.
Mhm.
But the collaborators, Dr. Kilin and Dr. Rasulev, are thinking aggressively in a good sense. They want to use it will be not equal share. For our part, we need less than 5 pages.
Okay.
Also, let me probably bring the older version of proposal to the I will bring it to the screen and quickly discuss the figures. So figure number 1 is perfect. I do not think anyone in the world can improve it. Figure number 2 will be candidate for removal completely. So if you describe it verbally sufficiently so that narration will not suffer of removing this figure will be great. And for figure 3, there is an idea to remove these labels, place these labels on their place to save space, and then move this segment into here so that it will be like five panels aligned horizontally, and then it will be more efficient use of space.
Okay, no problem.
Oh, thank you. Okay, anything else?
So,
yes, I'm listening.
Do we still need our old proposal for desorption of 2 ligands? Because right now we just described the absorption, right?
Yes. If you are very attached and think it is of high value, we can do it, or we can do it in our own proposal without collaborators. But for the project with collaborators, we do not need it.
Okay.
So we better focus on very narrow area and show the perfection, the best strengths in this little part.
Okay, makes sense.
I'm going to give a comment. It doesn't affect how you or I are writing, just bringing it up to the discussion that the collaborators, Dr. Rasulev and Dr. Kilina, will be solving a problem, how to merge this fragment to their fragments, and some how to say joint, some points of connection, some portals can be left to help them to do it, like some information about which data are going to be imported and which data are going to be exported to theoretical and experimental collaborators. You already mentioned it, but those are good gifts to our collaborators. That will make it easier to glue the whole piece, all pieces together and have it stronger.
Okay, makes sense.
Very good.
Yeah, I guess I'm going to send you an updated version maybe tonight.
Excellent. This is super. This is super. I've already shared a previous version with collaborators, with so, and they already started to write their segments because there is no time to wait. We need to like grow this building simultaneously and make arches between them at the last stage. But tonight will be a super timing, and it will be a big help for the whole team.
Yeah, I guess later we can go another iterations.
Okay. Okay.
Yep.
So among potential collaborators, who is your next target?
What do you mean?
I mean the Dr. Rengui Yang. There is no urgency, but if you like, proposal is definitely top priority. But
Yes.
if after you're done, if you try to build some models and make sure that they are reasonable, just as an introductory point, could be reasonable decision.
Yes, I will do some just preliminary calculations for them.
Yep.
At least to get some data points.
Because I invested very small time, but my model was not right. It missed some hydrogens and the gap was close. It is something that is not good.
Yeah, I will invest some time.
Good. For a little comment about figure that is on the screen right now. It I'm not sure that this transition is E22 because it is not symmetric. I would expect the blue line starting at somewhat smaller energy. Again, this doesn't affect any strengths of the proposal. It's just a little way for idealizing and make it easier to digest for reviewers. But for nanotubes, one would intuitively expect equal offset of this energies for electrons and holes from the Fermi energy.
Okay, so I guess in this language, E22 just means double the energy of HOMO to LUMO, right?
Yes, I'm going to go one figure back. So I would think it would be like this one, which is symmetric.
Okay.
This is very minor thing. It is not principle, but I was discussing it with one of the collaborators, and it was major criticism, not the methodology and results, but experimentally it is known that E22 transition is very intense, and even if calculations do not show it, it is where experimental excitations are going to.
Okay, I guess it's an easy fix. I can just rerun the MATLAB code. It's no problem.
Thank you. It's great. Okay. Do we need to discuss anything else now?
No.
Okay. Well, thank you very much for all this great help and for supporting Kevin with questions. Okay. Yeah. Thank you. Then I suggest we complete the session and I depart this electronic tool.
Okay.
Okay. Thank you. Have a nice evening.
Yeah, you too.
Thank you. Bye-bye.